Hey everybody, welcome back to another round of astronomy. Yeah, let's get going. We are now going to go and discuss the annular motion of the stars. So we've already talked about how do the stars appear to move on the order of hours. I go out at 8 o'clock tonight and look at the stars. If I go out at 9 o'clock, we'll notice that the stars have shifted by about 15 degrees to the west. And then night after, or after hour, those stars will continually shift. So now the question is, how about the yearly motion? How do the stars appear to change position through, let's say, the course of a month, or on the order of weeks and months? If I go out tonight on, I don't know, September 1st and look at the sky, and I go out again on October 1st, how does the sky appear to change? Okay. So that's what we're going to go into here. So leading question for you. Okay, we have the heliocentric view again, sun at the center, Earth orbiting the sun, and we'll do it this way. Let's say that I can take a giant paintbrush and paint the celestial sphere different colors and patterns. Okay. The question I have for you, for a person standing on the Earth at midnight, what region of the sky will they be able to see? Go ahead, take a second. You got it? Yeah, good. So we should be careful. What do we mean by midnight? Let's go to the opposite idea. If I said that it is solar noon, where is the sun located? Yeah, good. Solar noon would be the instant that the sun is crossing the meridian above the horizon. Okay. Incidentally, you also have noted that that would also be when the sun is at its highest altitude for the day. Okay. So what do we mean by solar midnight? Well, that must be when the sun is directly opposite the meridian, if you will. Okay? Yeah, good. So where would the person be? The person must be standing over here somewhere, directly opposite the sun. Okay? And I'll go ahead, I'll draw in a horizon for us. There's a horizon for us. And so anything that is, I'll say, for lack of a better term, below the horizon, or here, on this side of the horizon, that would be visible to somebody standing here on the Earth. Okay? So if you told me light green or dashed pink or dashed orange, perfect. Okay, good. We've got the right idea. Incidentally, I've been saying solar noon and solar midnight, right? Those are based on the position of the sun in the sky. Of course, more often than not, nowadays, we don't use solar noon and solar midnight. Instead, we use what's on our watch. Okay? And you'll notice this. Go out at noon and check the position of the sun according to your watch. Okay? And if you're sitting here in Indiana, you'll notice that for portions of the year, when you look at your watch, it will say noon, but the sun has clearly not yet crossed the meridian. Okay? And then other times during the year, when we're not on daylight savings time, you'll notice that the sun is closer to the meridian when your clock says noon. Okay, so we're back to the question. We've got an idea about the portion of the sky that an observer will see at midnight. Okay, good. So now the next question, let me move the position of the Earth. Okay. So let's rotate, let's pretend that the Earth orbits, I don't know, a little ways away. So the question, approximately how many days would have to pass in order to see, let's say, the green dashed portion of the sky at night at zenith? So go ahead, take a gander at that. Yeah, you got an idea? Good. Yeah. And the real question would be is, how far has the Earth traveled around in its orbit? Approximately. Okay. We'll say, hey, well, the Earth has traveled, we'll say approximately 90 degrees around in its orbit. Well, how many days does it take to travel a full 360? Yeah, that's what we define as a year. So we could set up a proportion. It travels 360 degrees in 365 days. Well, then how long will it take to travel 90 degrees? And we'll set that equal to x. We'll set up a proportion, and what we need to do is simply solve for the number of days. You could ballpark it. 90 degrees is about a quarter of the way around the circle. And so a quarter of 360, that's about 90 days. We'll say 91 days. Okay. So it'll take roughly 3 months until the dashed green portion of the sky is visible at zenith at midnight. Okay. So already we've got an idea about why does the sky appear to change over the course of months. It is not due to the rotation of the Earth, but rather the orbit of the Earth. Okay, good. Now, of course, we don't paint the night sky with these, colors. Okay? Right? It's not like it's dash cyan or dash blue or whatever. No. Generally, we can think of the sky as being lumped, divided up by constellations. Okay? And so this, again, is where we get, that's why those zodiac constellations tend to pop up. It's because those are the constellations through which the ecliptic plane can be found. You go out and you observe the location of the sun. It will be in one of the 12 plus 1 zodiac constellations. So the next question. Okay, so now we've got an idea about why the sky appears to change over the course of months. Now let's go a little bit more quantitative. Let's figure out by how much does it change for a given night. Okay? So here's a question for you. Approximately through how many degrees does the Earth orbit in one day? Go ahead, take a shot at it. You got it? Yeah, good. And again, how many degrees does the Earth orbit in an entire year? 360. So let's go ahead and set up our proportion. Okay? Right? If it does 360 degrees in 365 days, we'll ballpark it and we'll say that's roughly 1 degree per day. Right? So if we go out on day 1, or let's say day 0, the Earth will shift by about 1 degree the next day. Okay. So good, okay. Next question for you. Okay. So I've got a diagram here. Let me go ahead and walk you through. We've got the sun over here. I've drawn the ecliptic plane. That's in red. And I have drawn the direction of zenith for an observer on the Earth. So this represents zenith for the observer. Okay? So now the question, okay? Say this is day 0. Oh, excuse me, and this is the Earth's rotation. And I'll highlight rotation. So this is at day 0. Let's go out 24 hours later. Okay? 24 hours later, the Earth is going to be located at a new position. It's going to shift in its orbit by about 1 degree. Okay? The question I have for you, okay? For an observer, Okay? The following night, this is 24 hours later, for the observer standing on the earth, okay, will this specified star have already passed through midnight or zenith, is yet to pass through zenith, or is exactly passing through zenith? Yeah, you got it? Good. Well, one of these we can throw out right away. Okay? I've drawn the observer. Let's say 24 hours later, if the observer looks at zenith, they're looking in the specified direction that I have here. Okay? In other words, they are no longer looking with the star. They are looking, I'll say, above the star. Okay? So we can already X out, we can already say that it can't be exactly at midnight. Exactly at midnight, the person's looking over here. They're no longer facing the star. Okay? So that one we can X out right away. Okay? So now we have to figure out, is it before midnight or is it after midnight? And that's where we need to look at the Earth's rotation. Okay? Which way is the Earth rotating? So you can think of during this 24-hour span, the person rotates along, rotates, and at some point, they'll be facing here. And their zenith will be pointing at the star. Okay. Has the person rotated through more than 360 degrees or less than 360 degrees? Yeah, less than. They haven't quite finished the full rotation and before the star is at their zenith. So they've done slightly less than 360 degrees, which means it will be slightly before midnight when the star is going to be at the person's zenith. Yeah. Okay. You say, okay, well, how much is this angle? How small is this angle? Okay. We could go through and do a bit of geometry, but as it turns out, the Earth has shifted 1 degree in its orbit. That means that this person is about 1 degree shy of a full rotation. Okay? Turns out that 1 degree shy, so they've only rotated about 359 degrees before the star turns up back at their zenith. Okay, good. So we've got an idea that this star should pass through zenith before midnight. So the next day it passes through zenith before midnight. I've got another question for you. How long does it take for the Earth to rotate through 1 degree? Remember that this person has not rotated the full 360 degrees. I'd like to know, how long does it take the Earth to rotate that last 1 degree? Go ahead, take a minute, figure it out. You got it? Yeah, good. Let's just set up another proportion. Okay? And here we'll have to remind ourselves, how far does the Earth rotate in 1 hour? Yeah. Or if you prefer, how long does it take to rotate through 360 degrees? You could set up a proportion that way too. We could say 360 divided by 24 hours. Well, that would be 15 degrees in 1 hour. And we want to know, how long does it take to rotate 1 degree? X. Okay. You can set up a proportion, okay? Now, I'll admit that it's a little harder to do this in your head if you're thinking about hours. Let's think about minutes. So that's 15 degrees in 60 minutes. How long is that to take 1 degree? X. And now we see, okay, well, if we just flip everything, we get 60 divided by 15. That is, 4. So we'll get that X is equal to 4 minutes. In other words, this star will be at zenith for the observer on day 1 about 4 minutes earlier than the previous night. So if it's at zenith at midnight, right, 12 a.m., then the next day it will be at zenith at roughly 11:56 p.m., about 4 minutes earlier. Well, that means the next day it's going to be about 4 minutes earlier again, 11:52 p.m. And 4 minutes earlier as the Earth progresses in its orbit. Okay. Now, I don't care which one you prefer to memorize or have kind of locked in. You could say 4 minutes per day. I kind of like to think of it as about 30 minutes per week. I should put a unit in here. I tend to think of it as about 30 minutes per week, or you could say 2 hours every month. Okay. So go out tonight. You've got a new list, right? So number 1, practice your star chart. Number 2, you're going out and looking at how the moon changes position from night to night. Let's see. Oh yes, number 3, you're thinking about the phase of the moon and its respective location to the sun. Here's another one that I want you to start looking for, okay? Go out tonight, note what date it is, okay? Look at what stars you can identify from the star chart and where they're located with respect to the horizon. When you come out the next month, you'll notice that those stars will be shifted higher if you're looking to the east or lower if you're looking to the west. You are starting to observe the motion of the Earth around the sun and the consequences of that motion. Pretty cool, huh? Yeah, okay. So some summary slides. Nightly motion is due to the Earth's rotation and corresponds to about a 15-degree shift per hour of the night sky. You go out at 8 o'clock, boom, 9 o'clock shifted by 15 degrees. Okay. Again, due to the Earth's rotation. The annular motion or the seasonal motion is caused by the orbit of the Earth. Okay. And it shifts, the Earth shifts in its orbit roughly 1 degree every night. Because of that shift, stars will rise, or stars will reach zenith, or stars will set about 4 minutes earlier than the previous day, okay, 24 hours earlier. Okay. Corresponds to 4 minutes earlier, if you prefer, half an hour per week, 2 hours per month earlier. Okay. We can lock these two together and have a discussion about our calendar system. Okay? I think I'll save that for next time just to keep these lecture videos a little bit shorter. So hey, I thank you for your attention. Keep up the good work. I'll see you next time.